Good morning, good afternoon, and good evening, everyone. So today we're going to be continuing our applied linear algebra series, and we're now going to be going into lecture 9, where we're going to talk about different types of matrices. So far we've seen various operations of matrices. So we've clearly seen what a matrix vector product is, right? We've also seen what a matrix times matrix product is. So now we note that thinking of X as Rn, we see that this mat vector is between A and X, right? But it actually gives just a vector. So a column vector in Rn is equivalent to a matrix in R n by 1. Okay. We also saw the transpose operator if A is m by n. Then this is just a fancy way of saying their indices. Then it's transpose, we just switch the number of rows and columns. The number of rows now become columns, number of columns now become rows. And their indices switch as well. And then for X, if we transpose it, it becomes, so here we have n rows and one column. But if we switch it, now we have one row and n columns. So here's where we talked about a column and a row vector. But they do have the same components. But here it's important to note that the way we organize these vectors is actually important in how we multiply, in what we do with its applications. Because column vectors behave differently from row vectors. At least there are some rules we have to follow. Okay, what else am I going to say? Now we talk about inner and outer products. So we did talk about inner products, right? So here we see that this is a row vector multiplied by a column vector. So that's where that transpose comes in. And we even have this notation. You keep seeing this notation here. There's a 1 by what? What did I say? Okay, that's weird. I don't know why I said that. Anyway, so this is a dot product. And that's where we get the transpose from. Because we're doing a row by a column. If we do it the other way, that's not possible. It's not defined. If we both do it by column, that's also not defined. So again, this is one of those examples where it's really important to format your vectors how you need them to be formatted. And so that's where this motivates this notation, U transpose V. What if we switch the rows then? What if we do this? U times V transpose. Then we get this. We actually get this. So again, this is different from this. Or actually, wait a minute. Is it different? U sub 1. So again, here we go through row by column. If that makes sense. So we're going U sub 1 to Vn, U sub 2 V1 to Vn, U sub m V1 to Vn. Is that right? Let me see. This one we just have our usual scalar. We have a number. But here we actually have a matrix if we switch the rows. Interesting. So we would do something like multiply this u to this whole row vector, multiply u2 to this whole vector, then we keep doing it again and again, um to this whole vector. And we would get a matrix, right? I think that's pretty interesting. And what is this? This is the outer product. So it's u sub 1 v transpose, u sub 2 v transpose, u sub m v transpose. And there's this notation that we've probably seen in textbooks, the one with that circle with an X inside. Now we talk about special matrices. So last lecture, we saw two of them, right? So we saw the square matrix which is basically a matrix with the same number of rows and columns. Then we also saw this identity matrix, which is basically just a diagonal of ones and the rest are zeros. And there are different ways we could write it using standard basis vectors, which I've shown in the previous lecture. And here's the cool thing about identity matrices is that it will map any vector in Rn to itself. Now let me look at a permutation matrix. So if we take I and switch any of its rows and columns, we get a permutation matrix. So if we switch 1 and 3, so this is row 1, we switch this around, we would get that permutation matrix. And there's a notation for it. We switch 1 and 3. We would get that. Now let's observe what happens when we multiply that permutation matrix by a vector x. Actually, what happens is we switch the roles. So we get this resulting vector that's now in descending order, sub 3 to 1. And so here's a general idea of how we switch it from I to j. But yeah, writing this is way too long. But the idea is that we switch some row by another row. So here's a formal definition of a permutation matrix. If all of its rows and columns have precisely one entry, that entry is 1, and the rest are zeros. So we call that. So a permutation matrix can only come from an identity matrix. So here, this is a permutation matrix Y. It only has one entry in each row. So if you look at it row-wise, it's only one entry, and that entry is equal to 1. If we look at it column-wise, oh, I lost the 0. If we look at it column-wise, it's also one entry per row, and that entry is also 1. Now, if we do px, and then we switch these, this is just going to switch around, then we can actually determine what that permutation is. So we switched up here 1 and 2, and we also switched 3 and 4. Here we say that we have switched rows 2 and 4 from the identity matrix. So there's a permutation matrix. Okay, this one's an error, so I'm not gonna. It doesn't mean that if you have these two matrices, they're gonna be identity matrix. Wait, let me review that real quick. I know my professor made an error in that, but I know that's not the idea. Let me go to the lecture notes for 9, where we talk about special matrices. Where was it? Huh. Oh, this does give an identity matrix. Huh. Wait, can I try? So say we have I2, that's 1, 1, 0, 0, because we have two ones here, I sub 2. And let's say, okay, my permutation matrix is I'm going to switch row 1 and 2, because that's the only thing I can switch. This is going to be 0, 1, 1, 0. So if I multiply these together, those two permutation matrices should give me the identity. Is that true? Can we do a dot product? 0, 0, 1. 1. Oh, 1 times 0, 0 times 1. Then we do it again. 0, 1, 1, 0. 1. Oh, we do get it back. Oh, so apparently Now there was an error here somewhere. I just don't remember. When we multiply a permutation matrix where the rows have been switched with that same permutation matrix, we're going to get the identity back. And so the product of two permutation matrices is another permutation matrix. And there's a proof in the third homework, which we're going to go through. So that's a permutation matrix. Now a diagonal matrix tells us that, so we denote it as matrix D, D for diagonal. It's also a square matrix. And the diagonal, if all of its entries are 0 except those in the diagonal. So it's kind of like an identity matrix, but the difference is the entries could be any number in the diagonal when I is j. So 1, 2, 3, that's an example. And we can write it like this in terms of standard basis. We multiply it by x, we get this. We get a vector out of it. Okay. And that's it for that lecture. It was really smooth sailing, to be honest. Cool. Let's move on to the next lecture. I think we can move on from here. Okay, so this is an inverse of a matrix. So we talked about permutation matrices, we talked about identity matrix, we talked about diagonal matrix. And so now we talk about another special type of matrix, which is the inverse. And so what is this? So say we have a square matrix. We talked about, actually we didn't talk about inverse. So given square matrix A, it's invertible, meaning it has an inverse. If there's another matrix such that when you multiply that inverse by A, we get the identity. Okay? So it's the same thing as, remember, in calculus when we do functions, right? When we do compositions of functions, we plug in some input to an original function, we plug it then, that output, to some inverse function, we get back the original input. Same goes with matrices, where we multiply a vector by a matrix, and then we multiply that matrix by an inverse, and we get back the original matrix. And so A, the negative one, is called the inverse of A. Then now how do we get that? We'll go to it in a bit. Here we say, when we look at identity matrix, when we multiply an inverse, no, when we multiply the identity by the identity, we just get the identity. This tells us that I is invertible, and so that inverse is just the same as I. So what I'm saying is that if we multiply, I don't know, say this is I sub 2 multiplied to this, we would still get the same thing, right? Let me check. This gives me a 1, 0, 0, 0, 0, 1. Okay, yeah, gives me the same thing. It's invertible. And then for permutations, right? When we have the same kind of permutation, we multiply it to the same thing, we get the identity back. And this tells us that this permutation matrix is invertible. So its inverse is equal to its original. And for diagonal matrices, right, its inverse is just 1 over the entry. Because that would just give us identity, right? So if we do something like, say, D11, multiply it to 1 over D11, we would just cancel this, we would get a 1 back. That's why we just multiply it by its reciprocal. We just put the reciprocal of the entries. And then if we multiply those two matrices, we get the identity back. So that's when the diagonal matrix is invertible. It's not invertible, however, if the the indices are equal to each other, and that's zero, it's non-invertible because that would be undefined. Okay. Now, theorem 10.1 tells us if A is invertible, then A, its inverse is unique. In calculus, when we did root finding algorithms, to get f of x, to get y, we solve for f of x, right? X is input, y is output. To get back x, we solve for the inverse of y. Same thing with matrices. To get the b vector, we do a mat vec of a and x, some x vector. To get back that x vector, we do an inverse of a times b. And so here we kind of just review what we've done so far. A way to do it is through linear systems, solve that linear system, or we can use Gaussian elimination, which we've done in the past. And we're going to get solutions back for x, right? What else can we say? Yeah, so here we have an upper triangular matrix, or if you've been in my linear algebra series, we call this a matrix in echelon form. And so these are, they have pivots in every column, pivots in every row, linearly independent vectors, column vectors, I mean. There is a unique solution for x. Okay? As easy as that. And now we move on to lecture 11. So here, I don't know, what in the world we talked about? Why did it not say? That's funny. That is funny. We talked about inverse. Oh, we didn't talk about how to get... Actually, we kind of did already. It's just Gaussian elimination, right? Okay, let me see this one. Actually, before that, okay, yeah. You know, I'm gonna stop here because I'm gonna do a Python tutorial next on NumPy, which will tell us how to run code with matrices and vectors pretty much. So now we're gonna do some more computational mathematics in the next video. So I'll see you guys there.